Hey everyone, welcome to Lead Programmer. Today we are going to solve the question, make sum divisible by p. In this question, we have been given an array of positive integers nums, and we have to remove the smallest subarray such that the sum of the remaining elements is divisible by p. Let's understand this with an example. So in the first example, we have been given an array with numbers 3, 1, 4, 2, and we have to remove a subarray such that the sum of the remaining elements is divisible by p. So here, the first step would be to check whether the sum of the elements is already divisible by p, because if it's already divisible by p, then we would have to remove nothing, which means removing an empty subarray. Hence, we would return 0, because an empty subarray has a size of 0. But in this case, the sum is 10, which is not divisible by p, so we'll have to remove something. If we look at the array carefully, we would notice that removing 4 would make the sum of the array equal 6, which is divisible by p, which is 6. So there are two possibilities. We either remove this particular subarray, which has the sum of 4, and it's of size 2, or we remove this subarray, which is of size 1. Since the question asks us to remove the smallest subarray, we would remove the subarray of one element equal 4, and that would be the answer we return. A brute force way to solve this problem is to find out all possible subarrays, and for each subarray, we find the sum of the elements in that subarray, subtract that value from the total value, and check if the remaining value is divisible by p. If it is, then we know that that's one of the potential answers. We do that for all the subarrays and return the length of the smallest subarray. But doing so would potentially lead to a time complexity of n square or n cube. So can we do better? Well, the question itself gives us a hint. It mentions subarray. And whenever we see a subarray, we can think of a sliding window or prefix sum. So let's see if we can apply sliding window to the situation. So in a sliding window, we generally have 2 pointers, and we either increment the right pointer or a left pointer. So for the given problem, how would we determine whether we want to remove the left pointer or we want to move the right pointer? So let's put that aside, and let's see if prefix sum might help us better. We know that prefix sum is really helpful in finding the sum of the elements in a particular subarray. So for example, let's say we are given this subarray 3, 1, 4, 2, and the prefix sums over here would be 3, 4, 8, and 10. So we start with 3, 3 plus 1 is 4, 4 plus 4 is 8, 8 plus 2 is 10. And let's say we wanted to find the sum of elements between these for this particular subarray. So the answer would be 4 plus 2 plus 1, which is 7. But having the prefix sum, we can directly do 10 minus 3. So 10 corresponds to the index of 2, and 3 corresponds to the index to the right of 1. So we do 10 minus 3, that gives us 7, which is indeed the sum of this subarray. So would that be helpful? We see that it can potentially help us because we want to remove a particular subarray from the entire array such that the array becomes divisible by p. So having instant access to the sum of elements in a subarray might potentially help us. So let's explore this route further. So whatever we discussed till now, let's try to put that in mathematical terms. The main thing we discussed is we want to remove a subarray from the entire array such that it's divisible by p. How would we put that in mathematical terms? So first, let's say we have access to the sum of elements of the given array. So let's call it t, that is the total sum of the array. From that total sum of the array, we want to remove a subarray which can have the sum of, let's say, SS. After removing that, if we divide this value by p, we get no remainder, which means it exactly divides p. So the modulus of that value with p would be equal to 0. Now using the property of modulo, we know that we can bring this here and get t mod p minus ss mod p is equal to 0. And as a reminder, SS means subarray sum. So in the example that we previously saw, 3, 1, 4, 2, SS can refer to this subarray sum of 4, or it can refer to this sum of 4. Can we further break SS down into simpler components? Let's see. So bringing the prefix sum back, we get this. So let's say I want the sum of this particular subarray, what would the sum be? It would be the prefix sum at this particular index minus the prefix sum at this particular index. So let's call this index j, let's call this index I. So it's the prefix sum at a particular index minus the prefix sum at another index. So let's write it in those terms. So we get t minus p minus, let's say ps represent prefix sum at j minus prefix sum at I, and we do a mod p which is equal to 0. So let's expand this further. We would then get t mod p would equal ps at j mod p minus ps at I mod p. We can further simplify this like so. So we can have ps at I. So I basically got this term over here and this term over here. It's better to do a mod p of this entire term just because this particular term can be negative if the total mod p is greater than this mod p. So just so that everything remains positive, we can have another mod p over here. And there we go. In this equation that we derived, we know the value of p, we know the total sum of the array. The only variables that are unknown to us are I and j. And this I and j refers to the indices in the prefix sum array. So let's bring back the previous array we had. So one way to solve this is for each possible I and j in this prefix sum array, we can see if this equation is satisfied. If it is, then that's a potential answer. And if it isn't, then we can keep checking for all the values of I and j. But that would give us a time complexity of n square. So there's definitely an improvement that we would want to make. One observation is j is generally greater or equal to I, which means for each and every index that we visit, if we already have access to this particular value, then we can calculate this value and see if that equals this value. So what I mean is when we traverse the prefix sum array, for each index, we calculate the prefix sum at that particular index, mod it with p, and store it in a cache like a hash table. And for each and every index, we also calculate the value over here, and we see if the value calculated over here already exists in our hash table. If it does, then we know that we already found index j. So let's say we are at index j equals 1, and we find the value of the RHS term here. And if that value is already stored in our hash map, then we know that we have j, and I would be determined from the hash map. And hence we'd have I and j, and we would know the length. Using I and j, we can find the length of that particular subarray. So let's understand this further with an example before we move on to the code. So we would have a hash map. So initially, the hash table will not be empty. It would have one element where 0 would map to -1. The reason being, let's say we were to find the sum of this particular subarray. How would we do that? We would do that by taking the prefix sum at the rightmost index, which is 4, and subtract it with the index to the left of the start index. So this index to the left of the start index is -1, where the value can be a default value of 0. So to find the sum, we would do 4 minus 0, which is 4, which is indeed the sum over here. And the index can be -1. So let's say we were to find the length of this particular subarray, it would be 2 over here it would be 1 over here minus 1, which is 2. That's the length of this particular subarray. So let's start with the algorithm. So we start with a value of I equals 0. So as we mentioned before, we can find the value of the LHS term and store it in the hash table. So for I equals 0, we would have 3 mod 6, which is 3. So the hash table would have a value of 3, and that would correspond to the I value of 0, the index of 0. Next, we would find the value of the right-hand side with the same index over here. So let's do that. The prefix sum at j, so here j is also equal to 0, is 3. 3 mod 6 is 3. 3 minus 4 is -1. -1 mod 6 is equal to 5. So we check, is 5 present in the hash map? It is not, which means we haven't found any I and j value that satisfies this equation over here. So we continue. Now I is equal to 1. So the first step is to store the left-hand side value in the hash table. So 4 mod 6 would give us 4. So 4 corresponds to the index of 1. and then we find the right hand side value. The right hand side value would be 4 mod 6, which is 4. 4 minus 4 is 0. 0 mod 6 would be 0. Now check if 0 is present in the hash table. In this case, it is. This means that the subarray that forms between the indices of 1 and minus 1, which is 3, 1, if this particular, if the sum of these values, which is 4, is removed from the entire array, then the sum of the remaining elements would be divisible by p, which it is, because if you do 10 minus 4, you get a 6, and 6 is divisible by 6. So that's a potential answer. So we can have a result variable which says we can remove 2 elements, and it would make the rest of the array perfectly divisible by p. But let's carry on, because we want to know if we can find a smaller subarray which can also satisfy this property. So let's move on to 8. We first do 8 mod 6, which is 2. So we store 2 and map it to the index 2. Next, we find the value of the right hand side is 4. Is 4 present in the hash table? It is. Hence, we know that the subarray formed between the current index and 1. So it would mean that the subarray is itself, because if we write down the indices, this is 0, 1, 2, 3. Between 1 and 2, this would be the subarray that's formed, this element over here. And if we remove 4 from the entire subarray, we know that it would make the remaining sum divisible by 6. So since 1 is smaller than 2, we can update the result to 1 and carry on with the rest of the execution. So in this case, we just have one element left, which is 10. So 10 mod 6 would be 4. So it's fine if we update the existing element. So 4 can be updated to 3 over here, and then we can find the value of the right hand side. So 10 mod 6 is 4, 4 minus 4 is 0, 0 mod 6 is 0. And that would mean if we remove the entire array, so if we remove the so if we remove all the elements from the array, then the sum would become 0, and 0 is obviously divisible by p. But the size of that would be 4, and we already have a smaller size of 1, so we won't do that. Also remember, there's a condition which says that we cannot remove the entire array. So at the end, we would need a check which says if the result is equal to the length of the array, then we return -1, because the only way we could have achieved making the array divisible by p is by removing all the elements, and that's not allowed. So we return -1 as instructed in the question. So let's quickly look at the pseudocode. So we do the same thing. We first find the sum of all the elements, and if that is already divisible by p, then we can quickly return 0. If not, we first find the prefix sum array like we do over here. And to do that, we have a variable called current sum initialized to 0. And for each number that we visit in the original array, we keep adding that to the current sum and appending current sum to the prefix sum array. Next, we initialize our hash table or a hash map called tracker with the initial key as 0 and value as -1. We also initialize the result variable. Here we initialize it to float of infinity. We could have also initialized it to the length of nums, because the result cannot exceed the length of the given array, because in the worst case we remove all elements. So either is fine. Here I put float of infinity. Next, we go through each and every element in the prefix sum array, and we calculate the value of the left hand side of the equation and the right hand side of the equation. The value of the left hand side of the equation, which is over here, goes in the hash table, and we also keep track of the index. And the value we calculate from the right hand side of the equation is the one that we check. We check if that exists in the hash table. If it does, then we have a potential result which we can update. So we want to update the result such that the value remains minimum. So we do a minimum of the current value and the updated value from the tracker. And at the end, we return the result only if the result is not equal to the length of nums. If it is, then we return -1. So the overall time complexity of this algorithm would be big O of n. So let's look at that over here. Finding the sum in the worst case takes big O of n. All of this is constant. This would take big O of n, and this would take a big O of n time. So overall, the time complexity is big O of 3n, which is equivalent to big O of n. So the space complexity would also be big O of n, because prefix sum stores n elements, where n is the length of the nums array, and the size of tracker would be n plus 1. So big O of n plus big O of n plus 1 is equivalent to big O of n. So the time and space complexity is big O of n. Hope this was helpful. Don't forget to like and subscribe. See you later.